Today's lecture is going to be about neural network. My goal is to help you understand, to bring you inside the black box of a neural network. And by the end of this lecture, I anticipate that you'll be able to understand the mathematical underpinning behind this typical graphical representation of neural network. And you'll be able to see the correspondence between a graphical representation of this and the underlying matching multiplication. And then at the end, we're going to look at how we could visualize what exactly is happening under each neuron. And yes, hopefully you will have fun following this lecture, but make sure you download this Excel sheet. You can follow along if you want to. Let's start with this graphical representation of the neural network you might have seen in many different places. And this representation depicts a very small linear layer that goes from 3 nodes to 1 node. We'll see this line being drawn by connecting each of the 3 nodes to the next node, hopefully to produce a new output. Let's give it some number. So suppose we have 1 for my first input node and 2 for my second input node and -2 for my third input node. And before I can produce this number, we will have this weight. This node output node y has some kind of weight. And the weight is like on these edges coming in. For instance, I give 5 to this first connection, and maybe 3 to another connection, maybe 4 to another connection. To produce the output value, what we'll do is that we'll just multiply the input value with each of the weight. For instance, for first one, we get 5. The second one is 3 times 2, we get 6. And the third is 4 times -2 is -8. And then you add these 3 numbers together, which is equivalent to taking a linear combination or a dot product between the weights and input values. And you get 5 plus 6 is 11 minus 8 is 3. So our output value is 3. This simple network, that's what it does. Next, I'm going to show you how we could convert them into this matrix representation that I invented to help calculate this neural network through matrix multiplication. And this representation will be useful not just for studying, but also for prototyping new and advanced and state-of-the-art architectures. And you can see how that could be extended throughout the semester to a wide range of architecture we're going to consider, such as diffusion model, such as UNet, such as transformer, such as vision transformer and clip model, and so on. Okay, so but we'll start from the beginning of this very basic unit of linear layer calculation expressed in this matrix format, being able to go from the graphical representation from the left to the right. First of all, let me just draw some boxes to plan out where I will gonna fit these weights. And for input, I'll draw something similar for maybe use orange to match. So input, I will draw the other direction. 1, 2, 3. All right, and for my output is I would like for them to produce output in this way. So this is my plan. And if I were write this value for input is, well, right here, 1, 2, -2 here. And for the weight is 5, 3, 4. And to calculate this value, what I would do is that I could use this way to remind me how each input value is matched with a weight value in this case, and I will multiply both. They are connected by this guideline. So we have 5 times 1 is 5, 3 times 2 is 6, and 4 times -2 is -8. And we'll sum these 3 numbers together, plus 5 plus 6 plus -8, we get 3. All right, so this is how I would reformat the graphical form in the left to the right. Is this very compact matrix form. So we use mathematical notation. So W, we denote this weight as W, and we denote this input value as X. And then we'll also have this like small one, 2, 3 to denote that. We'll actually talk about the dimension of 3. At the end, we have this y is my output, and this is the equation for a linear layer is w matrix multiplied with x, which is input, and we get this y. So that is the equation, or y equals wx. So this is the format that you can see a lot. So the next extended to a slightly harder example with 2 output nodes. So in this case, I will try to connect each of my 3 nodes to my first input. So I do something like this, but instead of going directly here, I will purposely kind of take allow them to match individual weights before they go into my output. And for another one, this just reminds me of how this connection, each one is weighted by some number. So I have this weight 5, 4, 1, and 2, 3, minus 1. And then let me just give some input value again. 1, as I said, in this example, I have 1, 2, 1. And then since I have weights here, it's kind of hard to say 5, 4, 1. And then we'll compute this. 5 times 1 is 5. 4 times 2 is 8. 1 times 1 is 1. Okay, and for the next one, 2 times 1 is 2. 3 times 2 is 6. Minus 1 times 1 is minus 1. And we add them together. So 5 plus 8 and 1, we get 14 here. And 2, 6 minus 1, we get 7 over here. Then I'm going to write this correspondence matrix form. So I have this empty space, but I kind of map out in this way, use this guideline to tell me, well, I need to have this many columns, 1, 2, 3. But because of this y, we're going to get y here at only 2. So I have this. This is the size of my weight matrix. So I just draw like this nice form. And so let's repeat this equation. I have x, we have weight here, we have y. Basically, we like to calculate this linear layer as y equals weight and multiply by x. Okay, so then this time, instead of I'm writing out the answer, I will see whether I could implement using MathMul, the built-in match multiplication in Excel. So I'll fill some number 1, 2, 1, which is in my example. Now I'll fill this weight. So now it's kind of hard to see. I'm going to hide the ink so I can see the weight. So it's going to be 5, 4, 1, which corresponds to the first set of weight of the node y1. And the second is 2, 3, minus 1. So this is a practice to know how you could match the weights in the graphical form and also the metric form. Let's bring our ink back. So that's the correspondence. I basically copy all the weights over here to this matrix form. At the end, I was going to do is I could write match mult to perform a matrix multiplication. I'm going to select my weight matrix here, 2 by 3, and then comma, and going up to select my input column vector, then close parenthesis. Voila, I get 14.7. It matches the results I computed earlier by hand. Okay, we just look at going from the graphical form to the matrix form. So I like to go from the opposite direction. In this case, we have this 3 by 1 linear layer. So I want you to see this matrix form. You should be able to visualize in your head. That is a corresponding graphical representation here. I prepared a couple examples to allow us to practice that. So when we see this form with W and weight and Y, so first what I'm going to do is that I will have these 3 weights, 1, 2, 3, that correspond to this 1, 2, 3, 3 weights for my first node. And then I'll write 5, 3, 4. Those are my weights. And then these are sort of like linked in this way, mapping to the corresponding input dimension. They are 3 dimension in input, so kind of go this way. So you can see that this graphical, I try to purposely make them look very similar with visual cue to allow you to do matching very quickly. So in this case, let me just compute this one more time. So this 5, this is 6, this is 4, y 5 times 1 equals 5, 3 times 2 equals 6, and 4 times 1 equals 4. When add them out together, it's 15. Okay, and if I calculate this, it will be m mult, and using the Excel matrix multiplication, and select my column vector x, and then we get 15 as well. And then we can hide the ink. See, yeah, it is indeed 15. Open that again. Okay, so let's look at another example with 2 nodes in our output layer. So now we know with matrix multiplication, we just go ahead and implement this using the matrix multiplication function here and select this. Okay, so I'm selecting 2 by 3 weight matrix and also my 3 by 1 column vector and multiply them together. I get the result 15 and 6. And now I'm trying to draw the edges out. So as another practice, how do we have 2 sets of edges we need to draw? Let's just start from the first one. Maybe use my color pencil. 5, 4, minus 1. That correspond to these 3 weights. That should be part of the first output node. And I'll draw the first set of edge, 1, 2, 3. So it go correspond to this 1, 2, 3. How about my second set of edge? Let's use a different color so we could differentiate visually. So 2, 3, minus 1, my second set of weight, they correspond to my second output node over here. 1, 2, 3 over here, but you will put 3 minus 1. Let me just write it in. So commit this number into this location. 2, 3 minus 1. And for this one's 5, 4, 1. Let's just complete these edges. So then second set of edge the connection can go like this. So x1 goes to this way, x2 goes to this way, and x3 goes to this way, and which is this x1, x2, x3. Okay, complete this connection. Now I can just do real quickly. So this is actually going to be like 3 of this, and then this is this. Okay, and then how about this number? This number will be 1, 2, 2, which is about input in this case. So I could do this is equal and just select this, but it doesn't match the shape because I can transpose them. Okay. So this is a good practice for you to see the correspondence between these two forms that, come on, transpose. Okay. So 1, 2, 3. Column vector, but then when we use this canonical graphical representation, we have nodes going from top to bottom, and that this input data actually get transposed. So to fit in this representation, you can kind of think of it, you're trying to run your input more like sideways, but then you're put them down to the network in this graphical form in this way. And let's look at a bigger example here. Now we have 5 output nodes, okay? And how do we calculate? And we have a set of weights, 5 by 4 matrix in order to do that. You know, why is that size? So I will use this to just to visually show that is a required size in order for us to perform the necessary metric multiplication for this linear transform. So then if I will implement this, I will just use metric multiplication again and select my weight matrix and then select my input vector, which is column, and we get this 12A780, which I will write this over here is 12A780, and my input is 1, 2, 1, minus 2. There's some kind of process that allow us to map 1, 2, 1, minus 2 to 12A780. So that's what the linear transform means. So let's analyze just one particular the output feature dimension. For this, just focus on this one. So we have 4, 3, 2, 2. We have 4 weights here. Where do they go? So let's just extend this line to make sure that's where I'm gonna draw those 4 connections here, and then it will become 8. Where does this transformation correspond to in my graphical form to the right? So 4322, it turns out is just associated with my second node. So I can just write this 4, 3, 2, 2. And then if I will draw the connection, so these 4 lines correspond to this connection, these 4 connections that eventually get linear combined into my second output node, which is 8. And then we can just verify that calculation. So 4 times 1 is 4, 3 times 2 is 6, 2 times 1 is 2, 2 times minus 2 is minus 2. When you add it all together, it's 10, 12. It's not 10. Where did I make a mistake here? 4, 3, 2. Okay, 2 times 1 and minus 2 is 10. But oh, here it's minus 4. 2 times minus 2 is minus 4. Okay, it's 8. All right. So it's another example of why Excel calculation is much more reliable than my human calculation. But my human calculation is more relatable, I guess. You can see how I can calculate, make mistake, and correct myself. This is the best way to learn. Let's just consider another row. Hopefully, I won't embarrass myself one more time. So let's consider this another set of weight. Where do these four weights correspond to in our graphical form? It's going to be, let's use different color now, blue. It's going to be for force now. So this will be 2, 4, 2, 2. So if I will draw a connection here, so this four connection I wish to draw, and we're going to end up to this value, also 8. And then this four connection is going to be this way. I'm going to draw this way, and then all merge into this force nodes. Okay, and so that if we draw in this more complex form, it will be like this, I think. And then for red one is this. Okay, and then for this value, let me just fill in this input value will be 1, 2, 1 minus 2, and it produces 12, 8, 7, 8, 0. Okay, so that is an even more complex form for graphical representation as well. And if I have this complex form, I could just simply write code, do transpose, 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 and then I'll come here to select my output values, that 5 of them, and then I'll just put that direct direction. I can also do transpose and come over here and select my first input vector, and then close parentheses. And if I hide the ink, you can see that is how this input value and also the output value mapped to graphical representation in this way. And let's just calculate one more time. Can I replicate the calculation of 8? So this 1 times 2 is 2, 4 times 2 is 8, 2 times 1 is 2, and 2 times minus 2 is minus 4. And so this is going to be 10, 12, and 8. Yeah, okay, I'm correct this time. All right, so I'm kind of taking it slow now and trying to sketch as much as I can and use different colors, draw different lines, and to show you that it's just trying to enhance your understanding of the correspondences between the graphical representation. That's what you used to see a lot in paper and or in textbook, but then this underlying measurement multiplication is something you don't quite tend to see directly, but hopefully this way without resulting to a lot of equation, you can still see the correspondence, the batch multiplication visually. So if I can write equation, there'll be W, this is X, and this is Y, and it's going to be W, X, and which Y is the result of multiplying the weight matrix with your input X. Okay? All right, so now this is just linear layer. What if we want to add a bias term? Suppose if they all same weight. I did it on purpose because I would like to have a bias to be 0. I want to just show the effect of biases. Okay, so say we start with this maximum multiplication, just with weight, without biases, only weight, the same set of weight, and to the same input vector. You anticipate that they should give you exactly the same result, which is 15. But we'll like the bias to allow us to kind of lower or raise the output just by the amount of bias. How does it work? What we can do is that we'll basically just add this. Wait, I could just add by going to the left. Actually, I can use my mouse to help me select the bias column here. And then you can see instead of the first one, everything kind of raised by the amount of bias. Okay. And then for this one, it's a 327 network. I will do is transpose. Oops, that's not what I want to do. Transpose my output values. And this will going to be transpose my input over here and to take out this space, 3 to network. And okay, so this is a way they could add bias into your result, but this is not my favorite way to implement this. My favorite way is that I'm going to do a little trick by augmenting my input vector with an extra one. And the beauty of that extra one is that instead of this expression, I can just reuse my matrix multiplication. For instance, I'm gonna move this away, no bias. But now what I can do is that I can just extend my weight and biases into the single matrix, and then we can lower this to one position, take this one, and the result will be exactly the same as adding this bias vector into your output. And so if I will write out the equation, so y equals wx is the linear layer result bias. We'll add the bias term over here. That is a more straightforward implementation. But if I use this form by put weight and b kind of concatenate together in a horizontal way, and then we put x and then concatenate with just one extra one in the at the bottom vertical concatenation will give you exactly the same result. But we only have to write one matrix multiplication to perform this. All right, so there's biases. We'll see it a lot throughout the rest of the semester. There's, as much as possible, I will always use this way to add biases to the neural network they were discussing in the class. Next, we want to extend from just one example to two examples, and that there's a batch of two input. Now we have batch, this is a new thing I'm introducing. We are providing this network with two input. So the first is 1, 2, 1. Second is 2, 1, minus 2. And so, and then you can see that we can have the weight and bias look the exactly same as before. And the only thing that new is we extended my x, the matrix, from just one single vector, column vector, to a matrix. Okay, 3 by 2 matrix, or you can think of it as just two column vectors. And how do we compute the output then? In this case, we can just simply apply the same matrix multiplication, taking the weighted bias, and then select the entire matrix, and that was extended by one, extended with this extra one in order to make the bias work. All right. So it turns out when we have batch, we just kind of grow our matrix in this direction, and the weight and biases, they don't change. They use the same weights and biases. So if you were trying to rewrite that into graphical form, you might notice that I will just have to add nodes like this because I have two. No. This is actually one of the most common misunderstanding about how batch processing work, neural network. It turns out you have exactly the same set of the nodes. You can see this because we are sharing the same weights and biases. We're still talking about same four node, Y1, Y1, Y2, Y3, Y4. But what's different is that instead of having one row here in this transpose form, we have just two rows right now. So I can write down transpose and write down and transpose my input and also transpose my output here. All right. Now I can see that we are growing in this direction, but we are not growing the nodes. We are not growing this direction. No. Okay. It's still then same set of nodes. And then if we keep growing to the third input, what happened? Third input, another column. So the calculation is the same. Matrix multiplication, weight and biases. Input now it's a matrix, not just a vector. We have three column vectors, but it augmented with this extra one for biases. And then how about on the graphical representation? So you can see that the extension kind of go this way. So this transpose of my input. So for now, I'm still want to show you the corresponding graphical representation to help you build stronger intuition. But after this lecture, we will not see this graphical representation much, just because there's a lot more convenient to represent complex architecture using just matrix form instead of these nodes and the connections. Just as a review, when we talk about batch, we grow our matrices kind of into the right and horizontally. It has no impact on my weight and biases. And these are the trainable parameters. I highlighted and shaded in red and in gray to show you that this is the trainable parameters. Now, I would like to go from linear layer to activation layer. And we'll start with the most popular ReLU activation. So, but there's a little review of this linear layer. First, we'll start with linear layer. We'll do a maximum allocation, weight, and bias. And then I select my input, but I can select one more column, but it's not gonna work unless I add extra 3, 1 over here. Now I finish the first linear layer. What do we do ReLU? What does ReLU do? Intuitively, ReLU basically means that if I want to deactivate anything that's negative, only activate the node above 0. So what I find is that 3 nodes, they are below 0. I want to deactivate, and the result is that I just kind of cross them out. It'll become 0. So that's what I want to do. So I will just write it out. So it could be 0 in this 3 location. And then everywhere else, you just copy the value from previous layer, output from linear layer over here. Okay, so I just write them down just to, as a practice, reminds me your muscle memory that how the activation function work. You pass the same value except where they are negative. Okay, and so if I would implement it, the most common implementation is use max function. Suppose this is my y1, y2, y3, y4. I just change my notation. Instead of y, I can call it z, kind of before unactivated value, z3 and z4. And so I want y to be max of the z over 0 between these two. I will achieve this purpose. But then I'm going to use more advanced programming on Excel using map and also a lambda function that is functional programming. And so I'm going to now hide this ink a little bit. What I can do is I want to map is apply a function to every single location of this array. I'm selecting a 4x3 array, and my lambda function is going to be take x and makes x comma 0. So what this function does is that I'm saying I'm going to define this lambda function, and what it does is I'm going to apply max x to for every element. I just apply max of x comma 0, and as a result, we can get this result, which is the same as the one I just wrote down by hand. Another implementation is that we can just use the if and else. If greater than 0 and then x or x, something like this. Can we get right more clean? If x greater than 0, then we'll just keep x or 0. So this, I like to implement this when I'm learning this because it is closer to the logic we're trying to do. And max is more like very efficient implementation. So in this case, let me just repeat this as a practice. I will use my mapping function and I'll select my array, which is going back up to select the same array here, which is the unactivated output. And then I would write my lambda function, take x as my first parameter, but instead of using max, I use if x greater than 0, and I keep x, or if not, and 0, set it to 0. Okay, and 0, parenthesis, parenthesis, parenthesis. It'll give exactly the same result. Okay, so the second implementation is a bit more intuitive. The first is more commonly implemented in actual implementation in production. All right, next we're going to talk about a slightly more advanced version of ReLU. In the ReLU, we basically drop everything that's below 0. What if we don't want to just drop them? We want to give them a little negative value, a little bit change, just like, but then we just give them not as big as an impact. So that is leaky. Want that to leak in activation a little bit. So the leaky ReLU has this hyperparameter, not the parameter as in the sense of weight and bias that we train for. It's a hyperparameter. You can decide, say 0.1. Remember earlier we implement max is y equals max of z 0 But instead of just zero, zero means we have nothing. They allow us to think a little bit. We're going to put an alpha here, but alpha times z. In this case, if alpha is equals 0.1, it means that if you're negative, you only get a 10%, allow 10% of it to leak in. Okay, so in this case, I'm gonna use my map, and this implementation is very similar to what I just did. And max, actually, sorry, I type my lambda function, lambda with x, but I want to max. So x, this is exactly what I did earlier, x0. Okay, but instead of x0, I'm gonna move back a little bit to x alpha. Wait, can I can use my mouse to select alpha here. Okay, is alpha times x. Okay, but my alpha, I haven't put in the number yet because it's zero. And I put in the 0.1 here. Okay, so 0.1, you can see that in the -1, instead of becoming zero, become minus 0.1. Like -14, instead of becoming zero, become minus 1.4. And what else? -5 becomes minus 0.05. So what if you like to, if you give it one, what does it mean? It means just no effect. It's identity function. Zero, then you get the regular ReLU, and 0.1 is the leaky ReLU. And anything between zero and one is a leaky. Okay. What does it take to add a new layer in between? And we call it hidden layer. So this is what I have set up, what I want to accomplish. We have 3, 4, and activate 4, 1. This is the way that I want to change my dimension of the feature. So I have 3, 4, 1, and the graphical representation, you can see that as well. And so now we have to decide for my linear layer, how many weights and how many biases do I have? So for 3 to 4 conversion, what is the size of the weight matrix? If you don't remember, I will just draw this to help me. Okay, so I need 3. Okay, does it make sense? 3, and this going to be here this way. I need 4, and I can visually see that it's 4 by 3 matrix. That's all I need. And if I need bias, I just add another column over here. This is my bias. Let me make it thicker. Oops. 1, 2, 3, 4. This like this. Okay, this is my weight matrix and biases. And then next, how many biases weight do I need? So 4, we have 1, 2, 3, 4. So, and then for this is 1. So it will be 1, 2, 3, 4. Okay, and then one here for my bias. This is, I want to set this up so that, and then I could just so model this. One I can do is I can do rain array. Is create a random array of, now we can get this like the first parameter is rows, second is column. How many rows? We already mapped it out. 4 rows. How many column? 4 column, because 3 plus 1, 1 for bias. Then we have a bunch of random numbers to initiate this weight for. And then can do the same thing. Rain array. And what is the number of rows? 1. Double number of columns? 5. 4 plus 1. Okay, and then fill in these locations. And now we have that. I want to do my modification, but before I do that, let's just add little one here for allow me to do that trick. And for Excel, every time you modify something, get a new set of random numbers, so you can see the numbers are kind of jumping, but just okay. And then for ReLU, it's going to be map select whole array, and then lambda x max x 0. Okay, so this is my ReLU function. But then in this case, I don't see any result because no negative value, because everything, the bias is kind of too large. But anyway, at the end, I just do another measure allocation. So so then I'll get a linear layer, and then we can do the copy. We can transpose this. Then we'll get this hidden value, but these are before activation. Then fill in this value, and this is going to be transpose. Let me just do this. Transpose. Type this out. And over here. Okay. And then lastly, also transpose. So there's my Doesn't work. Type too fast. Okay, let's do it one more time. Transpose and 3 of this to allow me to fill the value. So this is my 3, 4, 1 with one hidden layer with 4 nodes. Okay. We just want to do one more thing. If we have one node, most likely it is for the binary classification problem that is this a human? Is this a face? And we like it to output to some value between 0 and 1. And for the last layer, the raw output z is the ranges from negative infinity to the positive infinity. We want this to kind of map into this. Sigmoid is a function that allows us to do that kind of mapping. And the equation of sigmoid function, sigmoid, is sigmoid z is 1 over 1 plus e to the z minus z's power. And so for this one, we'll implement this using the map and lambda function combination again. So I'm gonna select this and then lambda x. Then once you have this, it's a lot easier to write, implement your equation. 1 over 1 plus exponent minus x, okay? Is it enough? Okay. Then, okay, now you can see that something like 3, it becomes pretty close to 1, and something really 9. Both the rule of thumb is that if you're about like 3 and 4, it just kind of reaches 1. And minus 6, when you're below minus 3, minus 4, it gets 0. So you can see that this, we get the activation. Before activation and after activation, we can use this bias to kind of play with. What if we just keep adding biases? Eventually, everything is going to converge to 1. 20, okay? But similarly, if I take this down, I can see that all this probability value is going to go down. Eventually, everybody becomes so small, but never smaller than 0. And in classification, binary classification meaning that the probability is very low, okay? All right, and so I'm going to transpose into this one into my final output. This is my sigmoid. Now we talked about 3 different activation functions in this lecture. I have this plot to show you how that will visualize, but also as a review, how we can implement ReLU. ReLU is map, select this range of z from z. I can show you the most interesting range of these activation functions between the -5 and 5, because they can actually see the changes. So first one is going to be max x and 0. Okay, so this is my ReLU. You can see that kind of this is kind of flat below 0, but this is 0. Okay, that the x-axis, then the ticks is the numbers that are not correct, but this when you get the idea. But now they do a LeakyReLU. Let me copy this. But I'm going to move this up to here. All right, so this same ReLU, but now instead of 0, I just come back to add minus 0.1 times x. Okay, so you can see below 0, I can still have some value here left. And sigma is going to be, then copy this one more time. And then I move my x values to the top here. Okay, and then I can modify my equation. What is the equation for sigmoid? Sigmoid function is going to be 1 over 1 plus exponent minus to the minus x. This is my equation. Okay, so you can now have all 3 lines down here. We can visualize. So we have scroll out a little bit. So we have the ReLU here and LeakyReLU a little bit leaky down here, and with the sigmoid kind of between 0 and 1 here, the 1 and 0. And then most interesting kind of around here, between -5 and 5. That's where you can see some changes. So next, I want to show you how we could visualize what's going on. So I prepare a network, but we put some kind of a visualization space for it. You can see what it is. But it is actually 2 hidden layers like 2, and also output layer of 1. So this is my network. And I have 5 locations that I in my batch. If you draw on this 2D map, a 2-dimension x1 and x2, so it's going to be in the x1 is 5, 4, 3, 2, 1. It's actually going to put down here. This is a 5 particular data point in this space. I'm gonna just draw them for now. Okay. All right. For this one, I want to visualize what x1 looks like, x2. What kind of space that the neuron is actually describing, even though I just have 5 points right now to probe this space. But this is going to be just x1. We have done this exercise that we have this 2D coordinate. For x1, the x1 is at the bottom, this x1. So I select this. I want this one to be -5 and so on, like this. So you can see I just copy over actually. But actually, before I copy over, if I could fix the coordinate, it's hard to see. Let's just do this here. I want to copy this to everywhere, but I want to fix 269. That's where the x1 coordinate is. Once I have this, I copy and paste to all over this place. Then we can get this form. Similarly, we can do this for x2. I have this x2 to be only selecting x2 here. And then before I copy them over, I want to fix the here AB to AB, and then copy and paste over the places. So I have x1, x2 looks kind of differently. Okay, but you look at the 5 data point I sample for x1, you only have look at x1 is -5, -4, -3, -2, -1, which is the same as here. Okay, like here. And for x2, it's going to -1, 0, 0, 0, -1 is -1, 0, 0, 0, -1 over here. So it showed that this is x1 space and x2 space, but there are 5 different points we are considering in this case. Okay, now we have this hidden layer. What happened with a hidden layer? So this is going to combine 2 spaces by the weight of 1 and 4. And let's just zoom out a little bit now. This is the example I want to be. Okay. So I want this x1 to map over here, x2, and with a bias term. We looked at this before. And to visualize that space, I can actually implement this simply by this is equals my w1, w1. I'm going to come here and select my w1 times my x1, which is this entire space, and plus my second weight, and times my depth W2 space. Now I'm going all the way up to select this. And then eventually plus my bias term. I place my bias term here. Okay? So this is a space. You can see with 1, 4, 2, you have this looks like kind of like space. If 1, 1, 1, it looks like this. And 2, 2, it looks like this. So you can see how the space changes. And we can do the same thing for this. Let's just copy here and try to fix it. See what is easier this way. Just copy over here. Copy the equation, except that I'm gonna select the right thing. So I move my weight over here. The first weight to be second weight to be over here. My bias is going to be here. And my x1, because I copied the offset is not fixed, I'm gonna move over here. Now I can implement this. And there's a second layer. So I have 2 nodes now. 3, 1, 2. I just put some weight. You can also see the effect, just changing biases. This thing going to just move around. Okay, you can see that this is like this white line, which is the boundary of 0, like over here. And if you move the bias, you can see the result of that. But what if you really want that to be a boundary? That's when the activation comes in. You actually run the ReLU over here. You can see the result having ReLU. I'm just going to select this and mix with 0. Okay, but now I can copy this over to everywhere to implement mix over every place. And you can see that this shape, all the negative value that used to be blue now have been set to 0. That's the effect of ReLU. And if I copy this, I think it will work. Okay. And then I copy this over entire space. Now I can see that the blue part similarly is being reset. But let's just change some of the weights here to make the orientation kind of different, so it looks more interesting. You have two different spaces. Now, lastly, we can combine these two spaces. In this case, the combining is actually 1, 1, and with the bias -1. So that's easy to implement. What I'm gonna do is select the first weight times my x1 space plus the second weight times my x2 space, not x2, sorry, the second node, second hidden node. So this is the second hidden node, and plus my bias, and then we'll see the result combining these two spaces together. Maybe I have mismatched shape. Oh yeah, I have mismatched shape here. Let's fix this over here. Okay, now you can see that by combining these spaces, we generate this sort of the space. And lastly, if I just take this by implement a Sigmoid function real quick, which is 1 over uh, 1 plus minus this number. Okay, and select the entire, I think this array formula will work if I just select entire formula and just will map out this. You can see now it becomes a probability value in this region. And everything that's pretty big over here, about 5, it's all becomes 0. I mean 1, and down here is you have some kind of interesting probability mapping over here. So this is an example of having two nodes. I can visualize them, okay? And then we could change some weights. What if we could give more weight to my second hidden node? And what if I move the biases? So once you implement this, then it becomes a playground for you to play with different weights for the hidden nodes and also the bias. You could visualize results kind of like trying to learn these two decision boundaries, and then you eventually add them up together, and you have kind of being able to draw something kind of interesting. You can see that this is a result of putting this edge and this edge, right? Okay, thank you for listening. We'll continue with multi-layer perceptron, softmax, batch norm, and layer norm, and you'll see gradient descent as well. So hopefully things getting harder, but you can also get to learn a lot more.